Hello YouTubers and fellow hams. Well, this is part 2 in my series on 3D printing for ham radio. In part 1 we looked at the printer that I chose to show that there are a lot of low-cost options out there that come out of the box ready to go. And in part 2, this part, we're going to look at design and designing parts. The second big hurdle for most people that want to get into 3D printing. You know, you've got a part you want to make. Where do you start? Years ago, when I first got into 3D printing, there weren't a lot of choices. When you wanted to design stuff, you really had to use CAD software, CAD, computer-aided design. Programs like AutoCAD, which were way overkill for what I wanted to do, and had a huge learning curve. There were other 3D programs out there, mostly focused on visual arts, things like Maya, Blender, the open source Blender program, which would do visual things and graphics, you know, movies and videos and animations like Pixar does. There were other programs that had just started to show up for doing 3D stuff, like Google's SketchUp program, which was very popular. But these were primarily focused on visual production, on producing images, animations, and so on. As 3D printing became more popular, many programs were adapted to be able to output the files needed for 3D printing. Now, in CNC machining or 3D printing, there's an industry standard file format called STL, which stands for stereolithography. That's the 3D file that the slicing software is going to need in order to print something. Most of the CAD programs will output those files directly, of course, because they were used for CNC milling design. Google SketchUp did not have support for STL, and it was eventually added to it. So you could use Google SketchUp to design 3D models and then take them to your 3D printer. Blender, the animation program, also had STL output. Now the problem with these primarily visual programs is that they weren't designed for creating models for creating real-world objects. In the visual stuff, it didn't matter if the geometry was a little weird. One common problem was intersecting faces. You know, if you have a plane and another plane, in the real world they can't pass through each other, right? They're solid objects. In 3D modeling, it would be easy for that geometry to pass through like that. You know, you could have one plane that passed right directly through another one. And it wouldn't matter for visual stuff because when it was on an angle, the computer would just ignore that internal geometry. You know, imagine taking a cube, right, and putting a playing card into that cube. Visually, you don't care about the part of the card that's inside the cube. Right? There's a wall of the cube there, so you just render this outside stuff. But if you're taking that geometry and trying to slice it for a 3D printer or a CNC machine, the slicing software is going to see that internal geometry, and it's going to try to figure out what to do with it. And you can get by with that in some cases, but in other cases it just makes your printer do all kinds of unnecessary moves, and it can lead to messy objects, messy prints, and other issues. So you could use the visual programs, but it took a lot more work. Now, fast forward to today. Things have come a long way. Because of the popularity of 3D printing, there have been a lot of new things come out. On the Windows side, there's a really popular 3D program now called Fusion 360. And its STL export is smart. It knows that you're probably going to be 3D printing. It takes care of getting rid of that internal geometry, those intersecting faces. Another problem called flipped normals, which is, well, a plane inside of 3D geometry has two sides, right? And there's an outer side that you want facing out, and then an inner side that shouldn't have any properties to it. And sometimes those would be flipped, and the 3D printer wouldn't know what to do. It'd look like a hole to it, you know, a hole in a real object. So that's beside the point. But the STL export functions on some of these programs, they're smart. They know how to produce a proper model for a 3D printer to handle, and the slicing software that prepares it doesn't get confused. So things have gotten a lot better. What I'm going to look at, though, is I wanted to look at free software that covers all the platforms. So Windows, Mac, Linux, doesn't matter. And there are some complicated ones. There's FreeCAD, which is like AutoCAD. It's a very powerful design program, but that comes with a steep learning curve. There's OpenSCAD, which is a really interesting little beast. It's a script-driven CAD program. You actually, like writing in BASIC, it's very similar to BASIC, the programming language. You describe your objects, and then it creates the model for you and exports the STL file. Again, huge learning curve. But I found one example, and there's probably a couple of others, that's extremely easy to work with. Very easy for a person that has no CAD experience, no design experience, to get into and start creating parts to 3D print, and that is TinkerCAD. Now, TinkerCAD runs completely in your web browser, so it's completely OS agnostic. It doesn't care if you're running Windows, Mac, Linux. If you're on a Chromebook, it might even work on a tablet, although the controls would be kind of hard with the touchscreen. But yeah, it's possible. Anyway, TinkerCAD is so easy. I didn't look at any tutorials. I didn't read any documentation on it. When I first got the 3D printer, the first thing I did was I designed, where did I put it? I designed this little cap for SO239 connectors so I could put it on the back of my Yaesu when I take it in the field. And I did this in 10 minutes in TinkerCAD without any knowledge of how the program worked. It's that easy to use. So we're going to go over to the computer. I'm going to show you TinkerCAD, and we're going to make a part. And the part I'm going to make is going to be useful. Often in building projects, and you probably run across this too, I need little right angle brackets like this. Just a little right angle with a hole and another hole for mounting a display on a board or mounting a PC board in an enclosure. And I'm always making these by cutting pieces of sheet metal and drilling holes and bending them and trying to make 90-degree angles, and it's always just a lot of work. Well, we're going to design one in TinkerCAD. I'll show you how you can make it somewhat universal so you can resize it on demand, and then we're going to print one out. So let's go over to the computer, and I'll show you TinkerCAD. Okay, we're over here on the computer, and we're going to design a little right angle bracket. But first, let's take a look at TinkerCAD. So you go to tinkercad.com, and as you can see in the upper corner, this is made by Autodesk, same guys that make AutoCAD, so they kind of know what they're doing. It's going to look deceptively simple when we get in here, but let's just go in. Oh, first off, you do need to create an account. You need to register an account with it, and then you log in. But then you can create designs, and it will save them up on their site. And you can export the files as STL for your 3D printer or as object files for a 3D animation program like Maya or Blender. So I'm going to create a new design. And we will enter right into the workspace. Now the mouse controls, the mouse scroll wheel zooms. The right-hand mouse button lets you rotate. I recently got over some chest congestion, and I'm coughing a little bit now and then. I'll be doing that for a week, so I just decided I'm going to go ahead and make videos. Sorry about my voice. It'll get better as the days go by. All right, the right-hand mouse button lets you rotate the display around. You can see I can change my view. Left and right, let me turn it. Front and back, let me pivot it. The scroll wheel zooms, and if you click the scroll wheel button, you can physically shift it up and down with your mouse. And then the left button selects. All right, from left to right, faintly over here, you can see an orientation indicator. All right, front, top. That just gives you a reference as to how you're looking at it. Right, left. And you can think of that as the orientation of your printer's build plate, just to help keep things straight. So this would be front, I'm just standing in front of the printer and looking at the build plate. Think of it that way, and then it's easy to orient stuff. Over here you've got manual zoom controls. Fit all in view will shrink everything, so if you're zoomed in way too far, you can click that, and all your objects will shift into the view. And then home view takes you back to that original default orientation that we had. Across the top here, copy, paste, duplicate, and you can see keyboard shortcuts listed below. Control D for duplicate, that's useful. You'll use that one a lot, and we'll see why in a moment. Delete, undo and redo, of course, which is very useful. Up here we have grouping controls. Show all, group, where you group parts together, and ungroup. Align, which is very useful, and flip, so you can flip things around, align them and all. It's looking pretty simple, isn't it? It's very much like Legos, believe me. In fact, you can actually play with Legos in it and build build parts that way, but we're looking at building serious parts. Now, this is deceptively simple. You can create incredibly complex things in this, but you start with very, very simple building blocks. It's like Legos or Tinker Toys. I think that's where they got the Tinker and TinkerCAD from. It's so easy. Watch this. Okay, so I want to make this little bracket, right? Little right angle bracket. So I'm going to look at the part and I'm going to think about what shapes it's made of, right? How could you break this down into its tiniest primitive shapes? So what you really have, if you think about it, if you ignore this angle, you've got two flat surfaces, right? Well, they're not really flat, they have thickness. So you could think of those as cubes that have been flattened down. And that's what we'll start with. We'll take a cube and we'll flatten it down and make our plane for this shape. Now, how thick do we want to make it? This metal is really thin. This is probably 1/2 millimeter. But we're building in plastic, so we need some thickness to this, right? One thing you're going to want if you're doing parts design is you're going to want one of these calipers, right? And these, you can get them cheap. I got this at Harbor Freight for $10 or something. And it's digital. You hit the button there, and it's digital. Bring it over here, zero it, and then we can make our measurements. So, like, just out of curiosity, how thick is that metal? It is 0.5 millimeters. See, I figured about 1/2 millimeter. But with plastic, I'm going to probably want about a 2 millimeter piece, which is about that thick. So we'll start with a cube. Now over here we've got our shapes, right? And there's all our primitive shapes. There's many of the common basic shapes there. There's a drop down over here where you can choose additional shapes. Let me get my head out of the way. There's text, symbols, connectors, extras, circuit assemblies, and then something called shape generators. Shape generators, I'm not going to cover in this video. They're basically script-driven things that you can define and have it generate a shape. It's pretty cool. But we're just looking at basic shapes. And in those basic shapes, I'm going to take a box, a cube, and we'll drag that over here into our work plane. And we'll zoom in so you can see what I'm doing. Okay, our shape has properties. Over here you can see our properties. Is it a solid or a hole? A hole means I would use this to drill a hole in something else. For an example, let's bring a cylinder in as well, and I'll make it a hole. Now to resize things, bring this over where we can see the controls. Excuse me. You see these little white boxes that appear down here on the corner and one above? And when I mouse over them, we see a ruler appear with a number. and that's showing us how tall this is. This is 20 millimeters tall. This works in millimeters. Pretty much everything design-wise is going to work in millimeters for your printer. So you're going to have to work in millimeters. For the US guys, believe me, it's actually easier to work in a base 10 system of measure because you can do the math in your head. You know, if I have something that's 22 millimeters wide and I want to know where the center point is, well, it's at 11 millimeters, right? Because half of 22 is 11. If I have something that's 10 and 3/8 inches wide and I want to figure out where the middle is, I can't do that quick. So you're going to work in millimeters. So I'm going to make this cylinder. Now if I look at this bottom corner, you'll see that at the bottom it gives us a number that's this, and we can change that. Let's take that down to like 5, and you'll see it squashed our cylinder. And then we'll take this one down to 5, and it's now a cylinder again. And let's rotate it. Right above the cylinder there, you'll see a little curved arrow. That's a rotating on that axis. If I click on that, I'm going to rotate, and you'll see that it's putting the degrees right beside my pointer there, so I can take it precisely to 90 degrees. And then if I take it and I put it in the middle of this cube, oh, it's too short. Let's make it a little bit longer. Okay, if I put it in the middle of this cube, now I'm going to use the right mouse button to swing it around. That will become a hole through that cube once I group them together. I'll draw a box around here to select all of them and go up here to group, and it does the math, figures it out, and now we have a hole through our cube. Just that easy. All right, let's undo that. Undo. And let's get rid of that cube with the delete key, or that cylinder. Let's get back to making our bracket. I just wanted to show you how you can make a hole. Super easy. You can do that with any shape too. You can well, anyway, stay on topic, Kevin. So we've got our cube. These are the properties for our cube over here: length, width, height, so we can dial them in directly. Radius, that rounds off corners and edges a bit. So if I take that up a bit, now you can see our cube has soft corners and edges. I'm going to actually give it just a really slight radius, about 1 millimeter of radius, so that our bracket doesn't have pointed edges when we print it. So what was I saying about our bracket? We're going to treat each of these sides as a flattened cube, right? So I'm going to first flatten this down to 2 millimeters, which is the thickness I want to use. Okay? And then I'm going to elongate it. I'm going to duplicate this little right angle here, right? So I'll get my calipers, zero them, and one side is 14 millimeters, and the side with the elongated hole is 15 millimeters. Okay, so we'll grab our corner and we'll make this 14 millimeters. And then the width that I want to make it, let me pop back up to the full view here. This one's really wide. I really only want it to be about equidistant there, so that's 12. So we'll go over here and we'll make this side 12. And now we have, oh, sorry. I came over here and I made this side 12. Right? So now we have, well, it's still kind of square, isn't it? What happened? It's not square. Let's make that actually, well, no, 12, yeah. It's not square. So now we've got one side of our bracket. What do I want to do next? Well, I need the other side of our bracket. I've already got this to the dimensions that I want it to be, so I will do a duplicate, right? Which is this, or Control D. You can't see it, but there's now a second shape there that's identical to this one. If I use these arrows here to rotate, we'll bring that up 90 degrees. Now you can see that we have our second shape. Problem though is it's halfway through our build plane. It rotated around its center of axis. What we want to do is see this black arrow here. Let me move this down. See that black arrow that appears? That lets us elevate it up or down. And while I'm doing that, you'll see on the bottom of it there's a number. That's showing its edge or face relative to the build plate. So we'll take that up to 0, and now it's right there. Okay, now all we need to do is really just move it over so that the two are joined up at the corner. Let me rotate this around. We'll look at it from the top, and you can see we're not quite centered there. The arrow keys on your keyboard can be used to move it in steps, grid steps. And right down here at the bottom edge of the screen is Edit Grid and the steps, and right now it's at 10 millimeters. And you can change that down to as low as 1/10 of a millimeter or as high as 5. And if I hit the arrow keys, that's how far it's going to move the selected shape. So I'll use the arrows to bring that over. Another way you could do this, let me move it off center again, and I'll show you one of the really useful tools. If I select both of these objects, they're both highlighted in blue, there's a blue edge around them, they're both selected. There's an Align tool up here, Align. If I click that, these dots appear. I can now choose to center it this way. Boom! They're centered. Just that easy. I'll click away, and now I know that those two are centered. Okay, let's rotate this back around so we're looking at the side. The next thing I need to do is move them together. So I'll click on one of them, and I'll use the arrow to bring it in. Now they're joined up. Well, not completely. We've got to group them. They're still two separate pieces. But they're at least touching, right? Okay. I need to move that in just a little further. There. So now we're going to group these two together to make these two parts one part. So I'll select them all with a box. I'll go up here to Group, or you could type Control-G. And now this is one part. We've made our right angle bracket. All we need to do now is put the holes in it for our screws to go through. How big do those holes have to be? Well, let's take a look at this one. I'll zero my calipers, and we'll use this side of them, which has that little split here for measuring the internal diameter or something. And we'll measure our hole. And that hole is 4.3 millimeters. Yeah, we'll call it. Yeah, let's go ahead and go with what this told us. 4.3, right? Okay, so I've measured my hole with the calipers, and it's 4.3 millimeters. So we need to bring in a hole. We're going to use a cylinder to make a hole. And I'll bring in this massive cylinder here. Oops. Scroll out. And I'm going to resize this down to 4 millimeters. Now I want to size, I can do them separately like this, but I want to size them together. So I'll hit the Shift key, and now it's going to size them together. And I'll bring that right down until that number shows 5 millimeters, because it's going in 1 millimeter steps. All right. Our hole was 4.3 millimeters. 4.3. 4.3. So that should be our hole size, right? Here's a gotcha with 3D printing. The 3D printer has a very small nozzle. that's extruding the plastic. It's 0.4 millimeters, 4/10 of a millimeter in diameter. So what it's doing is it's spitting out a cylindrical bead of plastic that is 4/10 of a millimeter around. The software is going to draw your shapes and object using the center of that nozzle. So if you draw a circle with the center of the nozzle that's 4 millimeters in diameter, that nozzle is extruding a bead that's 4/10 of a millimeter, right? So from the center line of that nozzle, that bead is going to expand out on either side of it by 2/10 of a millimeter. What that means is if we draw a 4 millimeter circle with that nozzle, we're going to have 2/10 of a millimeter of plastic coming in. So we're going to have to add the diameter of our nozzle and figure that our 4 millimeter circle or hole is actually only going to be 3.6 millimeters in diameter because of that overlap. So what I do when I'm making holes or designing parts is I always take into account that that plastic bead's going to add 2/10 of a millimeter to every surface, every edge in a part. So what I want to do is make this cylinder, if I wanted it to be 4.3 millimeters, the hole that I'm making, I need to add 0.4 millimeters to that. And usually, just to be safe, I'll add 0.5 because that plastic bead is being squished down a little bit when it gets laid down, which expands it out. So, general rule of thumb, when you're putting holes in things, add 0.5 millimeters to the diameter, and what you'll actually get out of the printer will then be the right size. So, I'm going to add 0.5 to that. Actually, I'm just going to round it up. We don't have to be that precise. It's a screw hole. I'm just going to round it up to 5. And that's going to be our hole for the screw hole. So I'll drag that over into my bracket. And I need to drop it down so that our hole goes all the way through there. You can see it coming out the bottom. And now we need to align it. It's pretty close to center. But I'll select that, shift, and select that. I got them both selected. We'll hit the align tool, and we'll tell it to center it that way, and to center it, well, that's going to try to center it based on the whole thing, isn't it? That's all right. We can adjust that separately. We wanted to get it centered side to side. Now I'll just select my hole, and I'll use the arrow keys. Yeah, that looks about right. Right? That looks about right. Okay, so that's where one hole is going to be. Once I group those together, we'll have a hole. But before I do that, I need to put a hole in this side, right? And maybe I want this hole to be a little bit longer so we have some wiggle room when we're installing our bracket. So I'm going to take this hole, I'm going to duplicate it, and then we'll drag that up in the air so you can see that we've got another one. And if I take that, watch this, and I use the arrow keys and just bring it over to where it's right in the middle of our other piece, we'll have our slightly oblong hole. And let's make it just a little bit more oblong, shall we? Let's make it a little bit bigger, and we'll take the arrow, oops. Got to zoom in so I can grab that arrow. That's interesting. It's right where the rotate tool, there it is. No? Okay, come over here a second. Oh, I don't want to move it. I wanted to make it taller than 6. Let's add another millimeter, make it 7. Right, we'll bring it back in here. And we'll take a look at that from the side. Yeah, not quite where I want to be. I'm going to use the arrows to put that roughly in the center. and then we need to drop it down. That's what I was trying to do before, isn't it? Yep, that's what I was trying to do before. Let's take it over here and drop it down. About there. Yeah, that's about right. All right. Just like playing with Legos. Yep, I need to move that in a smaller increment. Let's take that down to 0.5 millimeter. Can't quite get that in the center with that. 1/10 of a millimeter. There we go. And now we need to center it left to right. Well, I can do that with the Align tool, can't I? So draw a box around those so they're both selected. Align. Hit that centered dot. Boom. And that put it in the center. Okay, so that's going to be our 2 holes in our right angle bracket. All we need to do is group the whole mess together to make those holes into holes. Draw a box around it. Group. It does the math. And now we have our right angle bracket. Look at that. To do this in a regular CAD program would have taken a lot of time. But as you can see here, it's just putting pieces together, just like playing with Legos. Okay, one other thing to consider before I send this to the printer. This is the way it'll show up on the printer right now. Now remember that 3D parts are made out of layers, right? Stacked on top of each other of extruded plastic. If you had a deck of cards, think of that as your layers. Okay, you got a deck of cards. What is a weak direction for that card, for that deck of cards? You know, if you put a force on the top of it, it's strong. But if you put forces on the side, those layers might want to separate, right? Or if you grab the top half of that deck of cards and pull up on it, those layers will separate and just come right up. So this part, if we printed this, is going to be made up of layers going down in this direction, all the way to the build plate. Do you see the weak point? On this right angle bracket, we need strength in this corner, right? This area here is going to have shear forces on it. Our part is going to be flexed in this direction as it's carrying a load. And if we have a layer going right across here, that makes that a weak point. It would be much better to print this thing laying on its side. That way the layers are going to be stacked down it in this direction. And it's going to be solid beads of plastic that follow the shape. So that's going to make this corner a lot stronger. So what I'm going to do is I'm going to rotate this guy over, now that it's all one part. 90 degrees. Oop, we're hovering above the board. Grab this arrow. And you can see the number down there in the lower right corner shows us how far above the board we are. Take that down to 0. And now I think our part is ready to print. It'll print in a strong fashion, being shaped like this. And we're good to go. So that's how easy it is to design something in TinkerCAD. I've made some pretty complex shapes. Like I said, I made this little SO239 cap in 10 minutes when I first hopped in here. This explanation's gone a little bit long, and I'm sorry about that, but you know, I wanted to be detailed. So anyway, I'll close the video out by showing you the printer printing this part and the end result when it's done. And in the next video, we're going to talk about what's involved in preparing parts for the printer. Slicing. That's the next step. You've designed your model. Now you've got to take it to the printer. It needs to be converted into layers and G-code commands that tell the printer what to do. And there's programs called slicers for that. So that will be part 3. Okay, let's go watch the printer print this thing. Well, there we go. I now have 6 right angle brackets that I can toss in my parts drawer and have ready to go the next time that I need them. You can see our nice little round hole and our elongated hole. So these will work just dandy. And they're pretty strong. I'm going to go ahead and try to break one. I'm sure I could do it. I'm afraid of cutting my thumb. They're pretty strong, surprisingly strong. This might even bend before one of these will break. They say PLA is not a very strong plastic. Well, maybe not compared to ABS, but I have found that in a lot of cases, PLA is going to work just fine for a lot of your projects. So anyway, I hope you enjoyed that. And the next video in the series, we'll look at slicing, preparing the parts for the printer. So stay tuned for that. Thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.